Alright, welcome to our continuation on lesson 2.3 where we're talking about the product and quotient rule and higher order derivatives. So last video we left off talking about theorem 2.9 and we did example 7. We're going to move straight into our next example, example 8. We are going to differentiate y equals 1 minus cosine x over sine x. But it also has another form, and we're going to differentiate that as well. The other form is cosecant x minus cotangent x. So let's start with the first form, 1 minus cosine x over sine x. That is going to incorporate the quotient rule we've been talking about. If we let's just always say rule of thumb, we'll let the top be our f and the bottom be our g. So we are going to first take the derivative of the top. Not the derivative of the top. Let me rephrase that. We're going to take the bottom, sine x. And we're going to multiply that by the derivative of the top. If we take the derivative of the top, 1 minus cosine x, the 1, it's gone. We'd have negative sine x, so we're going to have a sine x. Minus, we take the top, 1 minus cosine x, and we multiply it by the derivative of the bottom. Sine x's derivative is cosine x. And we put that over sine squared x. Well, now let's simplify it up. Sine x times sine x, that's going to give us a sine squared x minus, let's distribute cosine into 1 minus cosine x. So we're going to have cosine x minus cosine squared x all over sine squared x. And then we can distribute this minus into the cosine x cosine squared. So we're going to have sine squared x minus cosine x plus cosine squared x over sine squared x. Now, we a while ago talked about different trig identities. And I gave you a sheet with different trig identities. When we have sine squared plus cosine squared, that is equal to 1. So the derivative is going to be 1 minus cosine x over sine squared x. And there's nothing else we can do there, so that's it. Let's also find the derivative of that other form, cosecant x minus cotangent x. So, this is just a simple difference problem. So, we're going to take the derivative of the first term. Derivative of cosecant is negative cosecant times cotangent minus, then we take the derivative of the second part. The derivative of cotangent is cosecant squared which, if we actually were to look at this, they're the same thing. Because, let's just take a peek at what we got from that first one we did, because we're done with part 2. In that first one, we had 1 minus cosine x over sine squared x. Well, that's the same as 1 over sine squared x minus cosine x over sine squared x, which we can again rewrite. That first term, the 1 over sine squared, that's the same as cosecant squared. If we break up the cosine x over sine squared x, we can actually rewrite that term. I'm just going to do that over here on the side as 1 over sine x times cosine x over sine x. And if we do that, well, 1 over sine x, that's a cosecant x. Cosine x over sine x, that's cotangent. So from this, even though the order is different from what we got in 1 to what we got in 2, they give us the same thing. Pretty neat. Now we're going to get into the higher order derivatives part of this lesson. So, in our last chunk of videos in 2.2, we talked about the position function s of t. Being the position function. And then we also talked about how v of t is found by taking the derivative of s, and how that is the velocity function. But guess what? We could also find the acceleration from this. What we would do is we would take the derivative of the velocity function, which is actually what we call the second derivative of the position function. So this would be the acceleration function. So there's a bunch of different derivatives we can have. We so far have been talking about the first derivative, which we typically write as y prime. But you can have higher order derivatives than that. We can have second derivatives, which we write as y double prime. We can have third derivatives, which we write as y triple prime. We can have fourth derivatives, which we write as y. Now, we don't write it as 4 primes, we write it as a power. But then in parentheses we write a 4. And we can do that for any higher derivative than that, so we can generalize an nth derivative as y to a little power of n in parentheses. Now, they won't look like that. They'll look more like y4 or yn, and n can be any number really bigger than 3. Just because if we kept writing those little apostrophes after the y, it'd get messy. So this actually leads us into our final example for this part of our chapter. This is example 9. And it states, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is S of t equals negative 0.81 t squared plus 2. Where S of t is the height in meters and t is the time in seconds. We need to find the velocity and acceleration functions. So, we learned in lesson 2.2 to find the velocity function, we just find the derivative of our position function. So, v of t is going to equal s prime of t. And we know s of t. So if we find the derivative, what we're going to have is negative 0.81 times 2t, which simplifies to negative 1.62 times t. So there is our velocity function. To find our acceleration function, we're going to take the derivative of our velocity function, which is the second derivative of our position function. And the derivative of our velocity function is just going to give us a negative 1.62. So we've found both the velocity and acceleration functions, which wraps up lesson 2.3 on the product and quotient rules and higher order derivatives.